In this video, we will go over a very brief introduction to organic spectroscopy, talk about four main techniques, and set the stage for applying these techniques to study the structure of organic molecules. So generally, the word spectroscopy is defined as the study of how matter interacts with electromagnetic radiation, or light. And if you recall what electromagnetic radiation encompasses, well, it covers a very wide range of energies. So our visible spectrum is a small fraction of all the different accessible frequencies of light. So you can have on the left here very high frequency, high energy light. On the right here, low frequency, lower energy light. And all matter will interact with this light to produce kind of observable phenomena. In case we forget this equation, here it is. Well, energy is equal to wavelength lambda times frequency nu. And what that tells us is in the end there's an inverse relationship between lambda and nu here. So going back to the electromagnetic radiation chart here, the wavelengths on this side are going to be very small. The wavelengths on the right side are going to be very big. And so this is just important to keep in mind because in different forms of spectroscopy, the convention is to sometimes use wavelength, and the convention in another type of spectroscopy might be to use frequency. So we kind of have to wrap our minds around both those ideas. The value of spectroscopy is that by performing spectroscopy, we can measure spectra, and the spectra of molecules show us kind of the features that depend on exactly how the molecule is interacting with light. So three initial types of spectroscopy that are important to organic chemists are first the ultraviolet visible or UV vis type of energy, and then there's infrared energy, and then finally we're looking at kind of the nuclear magnetic resonance energy. The UV vis type of spectroscopy relies on what's called an electronic excitation, and what that means is that electrons in a molecule are being changed in their energy. So in an energy diagram, the molecule might look like this, where let's say we have the highest occupied molecular orbital and a lowest unoccupied molecular orbital. In an electronic excitation, we would shine light on this molecule. The molecule would absorb an amount of light equal to this amount of energy here. That would promote one of these electrons up to a higher energy level. And that absorption of energy would be detected. Turns out that for a single molecule, that energy gap is about 10 to the minus 20 joules. In infrared spectroscopy, what we are looking for is a little bit different. So one model of a chemical bond is to treat it like a spring. And so that's trying to reflect in the reality that atoms in a bond are actually kind of vibrating just a little bit. Mathematically, there's this kind of an anharmonic oscillator potential where in this kind of a function right there, the bond that we draw is at this kind of a distance r, but really it's able to kind of vibrate along the gray line there. So sometimes the bond is slightly longer, sometimes it's slightly shorter. And depending on how high in energy we are operating, that could be a wider vibration or a narrower vibration. IR is associated with an energy gap of 10 to the minus 22-ish joules, and so that tells you that's a smaller amount of energy than for UV vis. Finally, and maybe for me the most interesting type of spectroscopy, is nuclear magnetic resonance spectroscopy, NMR. This involves looking at the spin state of the nucleus of atoms. So there's a spin quantum number, but you can kind of look at that as being either up or down. And the way it works is we put our molecules into a massive external magnetic field, so that's called B naught here. And if this external magnetic field is pointed in a certain direction, that causes the nuclei that are pointed the opposite way to be higher in energy, and nuclei that are pointed the same way to be lower in energy. And that difference is what we can measure spectroscopically. It turns out that difference is about 10 to the minus 31 joules, so significantly smaller. So a fourth important technique is called mass spectrometry. So you'll notice the word here is spectrometry instead of spectroscopy. And the reason for this is because these two words get confused a lot historically and even now. But what people say is that the word spectrometry is used here because in mass spectrometry we don't use light to interact with matter. We're looking at something else. So it is kind of strange to call this unit organic spectroscopy and then put something that's not spectroscopy under it. But honestly, the main idea is really that we have all these techniques to study molecules. Anyway, mass spectrometry is used to measure the mass to charge ratio of ions. And by doing that, you can kind of figure out what the mass of the molecule might be. So here's an example of what's going on. So we kind of take neutral molecules and we kind of bombard them with really high energy electrons, and that will knock off one of these electrons to make an ion, and this is what would get detected. And using that, then you can get back to a mass of the molecule and then figure something else out with that. So those are the four main techniques, and what they're useful for is, in combination, we can figure out what the structure of a molecule is. So for example, a common process might be that you run these fancy chemical reactions with nice colorful beakers filled with, this crazy smoky gas coming out of it. You don't know what you made, and your question is, how do I know what I made? What is the structure, and what does the spectroscopy of this molecule tell me? So a general workflow looks like this. I will run a reaction. I will then run a MS, take a mass spectrum of my sample. That leads me to a chemical formula, right? Because I know mass, so I can kind of derive what a formula might be. Once I know the formula, then I can look at the IR spectrum of my sample. What IR is good for is it's good at looking at individual bonds vibrating, and so what that's super useful for is to look at what functional groups are present. So an IR of this chemical formula, of this sample here, might tell me that there's an amine, a benzene ring, and a ketone in this molecule. Right? Those would have very distinctive appearances in their spectra. And finally, NMR is most useful for kind of fine-tuning these results. So let's say I figured out these were my three pieces in the molecule, and I didn't know how to attach them with respect to each other around the benzene ring. Well, NMR gives us the tools to be able to figure that out. And at least in this case, let's say I could figure out that the pattern was supposed to be not like this or not like that, but instead the molecule here was my actual product of the reaction. So I hope that gives you a sense of the different techniques that we're using and the different types of processes that those techniques look at, and just very generally what information we can extract out of it.